So boiling point elevation follows the same pattern as freezing point depression. The change in the boiling point is related to the molality of the solution. So the molality of the solution times a constant. So that's the boiling point elevation constant, and that's going to be for the solvent. Because exactly what the solute is doesn't matter. It's just the number of particles. So we make use of the colligative properties, boiling point elevation and freezing point depression, when we put antifreeze in the radiators of our cars. So here's a picture of a guy putting antifreeze. Antifreeze is generally ethylene glycol, and it causes the freezing point of the water to go down and the boiling point to go up. So it expands the temperature range over which the water remains a liquid. And so that's a good thing for your engine. Do you need me to do this example?
Can you go back?
Yes, I can go back. It might be. Okay, so here's the equation for boiling point elevation. We're going to need the constant, so we would go to this table and look it up. There's the freezing point depression constant. Here's the boiling point elevation constant. For water, 0.512 degrees Celsius per molal, 0.512. So to do a problem like this, we'd have to look up the constant, which we just did. And again, that's not something that you would be expected to memorize. There's the boiling point constant. If we want to calculate the boiling point, see, I picked this constant because aqueous means that the solvent is water. So the change in the boiling point is equal to the molality times that constant. They gave us the molality. And we looked up the constant, so we just put these things together. 3.6 molal times the constant, bless you, 0.512 degrees Celsius per molal. And the molalities cancel out. So we get out the calculator. Now 1.84. So the change in the boiling point is 1.84 degrees Celsius. Is that the answer to the question?
No.
No. That's the boiling point elevation. It's asking what's the boiling point. Well, what's the normal boiling point of water? We should know this. 100 degrees Celsius. So do I add that to 100 or do I subtract it from 100? Add it. Add it. Because what this does is it makes the boiling point higher and the freezing point lower. It expands the temperature range over which it remains a liquid. So then the new boiling temperature is going to be 100, which would be considered to be an exact number, plus 1.84. So 101.84 degrees Celsius would be the answer. Any questions? Another colligative property is osmotic pressure. This is related to osmosis. We talked about that at the beginning of this chapter. Osmosis is the flow of solvent from a solution of lower concentration to a solution of higher concentration. The way I think of it is nature's trying to make them the same. The solute can't move through the semi-permeable membrane, only the solvent can. So the solvent's going to move to the more concentrated one, trying to even things out. So the semi-permeable membrane allows some things to pass, but not others. And this is an important concept because biological cells contain semi-permeable membranes. And so this is going on in our bodies right now, all this osmosis and things like that. So we can make an osmosis cell. We've got a U-shaped tube. When I was in college, we called these U-tubes, but that means something else now. So U-shaped tube. You guys didn't think that was funny at all either, did you? Man, I don't know, I gotta work on my jokes. So the U-shaped tube with the semi-permeable membrane. We put pure water on this side and a solution containing a solvent on this, a solute on this side. I'm just gonna call it salty water. And the water can move back and forth through the semi-permeable membrane. And so it's going to move towards the salty solution. And what's going to happen is the level of water on this side is going to rise up. And then this side has to come down because the water is transferring from one side to the other. If you remember back in chapter 5 when we talked about gases, we had a thing called a manometer where we measured the difference in the heights of the liquids, and that reflected a difference in pressure. Right? So here, the pressure outside, these are both open to the atmosphere. The atmospheric pressure is the same above it. So what's going on here, and how does this relate to osmotic pressure? Well, you can measure this difference and relate it to a pressure, and that is the pressure you would have to apply to this side to prevent the osmosis from happening, to keep the levels equal. That's called the osmotic pressure. So osmotic pressure is defined as the pressure required to stop the osmotic flow, to keep those levels even on each side. So here's the equation for that. It's this is capital pi is the symbol for osmotic pressure. This is equal to the molarity times the ideal gas constant times the temperature in Kelvin. And here we're going to use the same value of the gas constant we used for gas laws, 0.08206 liter atmospheres per mole Kelvin. And we're choosing this one because of the units. They work out nicely. Okay? So we can calculate the osmotic pressure of a solution containing 1.5 grams of ethylene glycol, antifreeze, in 50 milliliters of solution at 25 degrees Celsius. So osmotic pressure, we need the equation. Capital pi equals the molarity times the ideal gas constant times the temperature. Looks like Mr. T.
That was pi in the beginning?
Pardon me?
That was pi in the beginning? Or?
Yeah, that's a capital pi. Pi is a letter.
Osmotic pressure?
Just this is a lowercase pi, and this is a capital pi.
Is there a difference between the two?
There is. The lowercase pi is 3.14159, right? Related to the geometry of a circle.
Yeah.
This is the Greek letter pi, and we're using it as the variable for osmotic pressure.
Oh, okay.
Yeah, and there's, yeah, like she said, just let it happen, it's okay. We had pulling in all these Greek letters. We ran out of English letters, okay? And so, we've got the chi and the psi and the phi and the theta and all these different things. I am not making crap up. When I make up crap, it's much more interesting than this. Like the Quantum Hotel, right? Yeah, that was a little more interesting. I guess a little, yeah. Anyway, we're going to do this problem now. So molarity, we need the molarity. Did they give it to us?
They gave you grams.
They gave us grams. Yeah, so we can figure it out. So I'm trying to write with an eraser. Okay, so we need moles of solute per liter of solution. Well, they gave us grams of solute. 1.50 grams of ethylene glycol, C2H6O2. So we need the molar mass of that so that we can convert that to moles. So we've got 2 carbons, 12.01. And we've got 6 hydrogens, 1.008, and we've got 2 oxygens at 16 each. And so we get 62.0 7. So we got 1.5 divided by 62.07. 0.0241. I have 3 significant figures in this initial number, so this is going to have 3 sig figs, but I want to carry 2 extras because I really hate rounding errors. So there's the moles. So that goes on the top here, 24166 moles. And what's the volume in liters? 50 milliliters. Is that 50,000 liters or 0.05 liters? 0.05. Some students just, I don't know, they get that mixed up a lot. If you're one of those people, just write the conversion out so that you get it correct. Somebody on the exam yesterday was doing the conversion backwards, saying that 13 liters was 0.0013. It was a mess. Anyway, don't do it. So we've got this number divided by 0.05. So the molarity is 0.483. That's an 8. And 2 extra digits. Moles per liter. Okay, so now I've got the first term for the osmotic pressure equation, 48333 moles per liter. Not a good idea to use the capital M abbreviation in the calculation because you're going to forget that it's moles per liter and you're going to screw your units up. Then I need the ideal gas constant. So 0.08206 liter atmospheres per mole Kelvin. And if you forget that the temperature should be in Kelvin, this should be a clue that there's Kelvin down here. So 25 degrees Celsius would be 298.15 Kelvin. And then we check our units. The kelvins cancel, and the moles cancel, and the liters cancel, and we get atmospheres, which is a unit of pressure. How convenient. Okay, so this times 0.08206 times 298.15. My osmotic pressure is 11.8 atmospheres.
Why in Master in Chemistry and in the book it doesn't do 273.15, it just does 273?
Because they're stupid. Yeah. Yeah, they round it, and I don't think it's a good idea. I think just the extra 0.15, I mean, that is what it is. The conversion is Celsius plus 273.15. If you don't have decimal places in your temperature, then does it end up mattering? Not really. But sometimes we do have decimal places, and so then it can matter. And so I think it's best to just use the full value. It's a good question. Is this a high pressure? Yeah. Almost 12 atmospheres. That's a really, really high pressure. I wouldn't want to be around a container that had 12 atmospheres of pressure on it. That's a lot of pressure. But the osmotic pressure tells us that to keep this, this solution from migrating, keep the water from migrating into this solution, you'd have to apply a pressure of almost 12 atmospheres to stop it. Otherwise, the water's going to come over. It's crazy.
You could actually make that go reverse osmosis.
You can. You've heard of reverse osmosis, right? What do they use it for?
Desalination.
Desalination, purifying water. So reverse osmosis, you put pressure on the side where your tap water or your unclean water is, and you force the osmosis to go in the reverse direction. And so you're pushing the water through the semi-permeable membrane, and you're getting pure water on the other side. When you look at this solution and see what a high pressure you'd need, you can see that this would be difficult to do on a solution that has a high concentration of solutes, like seawater. It's going to require pressure, and that's going to take energy. Doing it on tap water is going to be easier because the amount of dissolved solids in tap water is much less, and so then the osmotic pressure will be less as well. Good question. Any other questions?
I have one that's a bit out there. And
Go ahead.
no, it's-
No? Okay.